All right, I think you guys should now have permission to record. Let's see. I think we should start slowly, and the others will join if they are going to join. All right, let me also. All right, let's get started. And the last time we discussed left pause for localizations. Let me scroll here to show you what we did last time. Yeah, we defined the Czech local. Can we define the Czech local model structure? Actually, I already forget. Where exactly did we stop last time? Anybody has notes from the last time, just in case? Did we define, here's a question, did we define the Czech local model structure last time? I'm pretty sure we did, right? I mean, it's, maybe not. Anybody has notes from the last time, guys? Or maybe not. Let's see. Okay, I will assume we could define it because I think I remember defining it. But just to remind you, the Czech local model structure and simplicial pre-sheaves is defined as the left boundary localization of the projective model structure. So the projective model structure has as vibrations and weak equivalences the object-wise vibrations and object-wise weak equivalences. And you do a left boundary localization of this model structure on with respect to the set of all morphisms which are given by the Czech nerves of good open covers of an element in the site. So the existence of such a model structure is a consequence of the Smith's theorem for Bowles localizations. And the weak equivalences can be described as stockwise weak equivalences. So let me remind you that for sheaves or pre-sheaves on the Cartesian site, you can compute stocks by taking n-dimensional open balls of radius epsilon around the origin in Rn. Then you let epsilon go to 0, so you construct a diagram of shrinking open balls, and you check its co-limit. And that's the stock, the n-dimensional stock of a pre-sheaf on the Cartesian side. And a nice description of local weak equivalences of simplicial pre-sheaves on Cartesian side is that these are maps that induce a weak equivalence on all n-dimensional stocks.
Is it immediately clear that this holds?
No. It's not immediately clear, and it's something you must prove separately. In fact, some of the proofs in the literature you can find, maybe here's one reference, I think it's fairly readable. There is a book by Amabel, Gabriel, and Hay. It's called differential cohomology. And it does have a considerable amount of material for about sheaves or infinity sheaves on the Cartesian side. In particular, it does prove the property about stocks. Yeah, so, but it's true in our case. I mean, of course, it's not true in general because there may be sites out there that don't have points, right? Formally speaking, a point on a site will be a functor that behaves like a stock functor, in a sense like it's a functor from your infinity category of sheaves to the infinity category of spaces, for example, simplicial sets in the Kahn-Quillen model structure. And this functor must be a left adjoint functor and it must preserve finite limits. So that's called a geometric, well, I guess, the left adjoint functor of a geometric morphism of troposes. And there are troposes out there, categories of sheaves or infinity sheaves that do not admit any such functors. And of course, in this case, you will not be able to describe the local weak equivalences as stockwise weak equivalences. Instead, you would have to use more sophisticated descriptions. For example, you could also describe local weak equivalences using the local Whitehead theorem if the tropos is what is called a hypercomplete tropos, which many troposes are yep. So there are many criteria. Some of them are less practical than the others, and for our purposes, of course, the stockwise weak equivalences is by far the easiest description. And finally, fibric objects. So fibric objects in any left Bowles field localization will be precisely fibric objects in the original model category. So in our case, that's simplicial sets. So these will be pre-sheaves of Kahn complexes, which also satisfy the descent condition with respect to Czech covers. And I think last time we actually tried to consider the examples. Yeah, we saw how the Czech map induces the descent map. In fact, we also considered a simple example of open covers with two elements. And we saw how you obtain from the Czech nerve, how you obtain was it somewhere here? Oh no, I think it's here. Yes. So basically, by mapping this pre-sheaf into F, you will see a homotropy pullback, which is precisely the descent object for this open cover. And even more generally, mapping the Czech nerve gives you one implementation of the simplicial set of compatible families over this open cover. Yeah. All right. And we also consider the examples. Some examples were de-loopings of Lie groups. We wrote down the descent object in detail, and we saw that the descent object gives rise to the transition functions for a principal G bundle. So as you can see, you recover the description of principal G bundles over X, the manifold you are mapping to BG with respect to some good open cover of X. So that's you see that mapping any manifold into BG allows you to recover the groupoid of principal G bundles over X. And the nice thing about this definition is that in the same manner you can define a principal G bundle not just over a smooth manifold, but over any X that is an object in your category of simplicial presheaves. And you think of such simplicial presheaves as geometric objects, and you can start mapping them into BG. So this left side is of course cyclically the same as the derived mapping space from X into BG, which allows you to replace X with any simplicial presheaf. And in this case, the role of a good open cover of X will be picked up by the cofibrant resolution of X in the projective model structure. So the cofibrant resolution will be a Czech nerve-like object which resolves X as a cofibrant presheaf. So it will be a degree-wise coproduct of representables, basically, that kind of behaves and looks like a Czech nerve of some open cover of X. Yeah, so you can already see the advantages of the technology of simplicial presheaves in that they allow you to define things that previously were difficult to define and difficult to prove or work with. And here, everything comes out automatically. All right, so that's what we did last time. And today, I want to illustrate this with another example, illustrate the technology of left Balanced localizations with another example, and which is the example of Siegel gamma spaces, Siegel delta spaces, also Siegel categories, complete Siegel spaces, basically all the objects that have Siegel in it. And here the goal is kind of similar in all those cases. We want to encode some homotopy coherent structure. For example, maybe we want to encode an ordinary monoid, but in the category of spaces, and which is associative and unital not in a strict way, but perhaps in some homotopy coherent way. Or perhaps we could do the same, but with a commutative monoid. So these will be encoded respectively by delta spaces and gamma spaces. Other things we may want to encode include groups, categories, and categories, and so on. And these will be also encoded by group-wide gamma spaces, Siegel categories or complete Siegel spaces, and categories will be ultimately encoded by complete n-fold Siegel spaces, but maybe that's a story for the next time, not today. And from a historical point of view, there were two approaches to defining such homotopy coherent structures. The approach by, well, I guess I would say that was pioneered by Skashev, but then picked up by many others, including May and Gay and other mathematicians, is what I would call the algebraic approach. So the algebraic approach says we are going to encode, for example, our monoid M as perhaps as a space equipped with a multiplication map, and we will try to impose the usual associativity constraint. Let me try to see if I can figure in here. So I can either multiply the first two factors or the last two factors. And then I can multiply one more time. And if this diagram was strictly commutative, this would encode the usual associativity of a multiplication. But if you are encoding some kind of a homotopy coherent structure, then you can say this diagram commutes not strictly, but up to some homotopy, which I denote by this letter H here. And the homotopy will be encoded as part of your data. So not only you are going to write down an underlying object M, a multiplication map from M times M to M, but you are also going to write down a homotopy as indicated in this diagram, and this homotopy will be part of the data. And as you can guess, the story doesn't stop here. Of course, this homotopy itself will have to satisfy additional constraints, which would themselves have to be encoded as a further data over higher homotopy, and the process will continue indefinitely. And I think Skashov was one of the first to write down an explicit example of such a construction using what he called an infinity space. Eventually, this was all codified by May as algebras over operads. And this approach works. I mean, it's not a bad approach, but perhaps today we can point out that somehow it's in many practical examples, it's difficult to explicitly write down all this data that we have to write down, such as all those operations and higher homotropies between them. This just may be too difficult in some examples. So Skashev's work, I think, came out in 1960s, and somewhere around 1970, Siegel came up with his own approach to homotopy coherent monoids and other structures, and this approach is called gamma spaces or delta spaces or some other names. And its technology, so previously we were encoding the structures as algebras over operads. Here they will be encoded as presheaves on a certain category, and these presheaves will be equipped with a model structure given by a left-Bowles-Wilk localization of the projective or injective model structure. And as you may already guess, we are big fans of the functor of points approach in this class. And this is one more application of the function of points technology. And we'll see how exactly a bit later. Yeah, so let me summarize what I just already briefly mentioned in some way. What are the pros and cons of the what I call the algebraic approach? And the perhaps we can call it the geometric approach. And the main differences is, well, one of the main differences is how colimits have a vastly different level of difficulty of treatment. For infinity spaces and other highly structured algebraic entities, colimits are just very difficult to compute. Whereas for the setting of delta spaces and gamma spaces, colimits are computed object-wise. And this also continues to hold for homotopy colimits. So you can already see a drastic difference in the level of difficulty. And of course, at this point, you should be wondering if, so these two descriptions will be equivalent in some way. And we'll later see ways to phrase this precisely as a equivalence of model categories, for example. And if they are equivalent, you may ask, well, why is it that in one case colimits are difficult, and in the other case colimits are so easy to work with? And where exactly is the difficulty hidden when we pass from one model to another? And maybe one answer here is that the main difficulty or the main technicality here is hidden in the localization functor. So in fact, you could say colimits are object-wise, followed by the localization functor. However, this last step is not necessary because the map from any object to its localization is a local weak equivalence, which means it's optional if you stay within a model category. It's not necessary to replace an object with a weakly equivalent object. I mean, they are weakly equivalent, so for our purposes, they will be treated the same. And however, in the algebraic setting, you do not have such a luxury because here, in a sense, you could say that objects here are in some sense already defined as local objects. And since they are forced to be local objects from the very start, you are forced to apply this localization functor every time you compute a colimit. And that's why colimits are difficult in the structure, in the algebraic setting. And I also listed for you some other reasons why.
As I understand, the main difficulty lays in theoretic language about colimits that they have in algebraic approach. Yes.
Well, yeah, you could say, yeah, I mean, of course, that's the fact, the definition of an algebra over an operag is what makes colimits difficult, yeah.
Is a problem, yes, to define colimits in this case.
Well, colimits exist, they're just very difficult to compute. That's the point, yeah. I mean, it's you can look in some papers by that construct model structures on operads and see how those papers compute at least some colimits in the category of operads. It's not easy.
The main difficulty in computation of them, yes?
Well, yeah, I mean, it's conceptual, of course. These models are equivalent. So whatever difficulty you will be having will be, of course, connected to a specific choice of a model. All right, so for similar reasons to colimits, cofibrancy, or being a cofibrant object, is a vastly different condition in the two categories. Here, cofibrancy is actually quite difficult. It's roughly like being a free object. Here, cofibrancy is basically object-wise.
Please, if you don't mind, may you reveal a bit more about cofibrancy in algebraic approach also?
Oh, we didn't actually talk about it properly, but typically, so in the algebraic approach, the model structure is the transfer model structure. And in pretty much, well, in any transfer model structure, you can give an explicit description of cofibrant objects as more precisely, these will be retracts of free objects. And free objects are not so easy. There are not so many of them, and they have a fairly complicated structure over operads. Imagine, for example, I don't know, like a free associative algebra or even a free commutative algebra. The free commutative algebra will be just the algebra of polynomials. So in the model category of commutative differential Gregoric algebras, for example, you will only see retracts of the algebras of polynomials as cofibrant objects, which of course it is possible to construct such cofibrant resolutions. That's what homological algebra does for you fairly efficiently. But it's of course not as easy as in the case of Siegel gamma spaces. So that's a different story. So in the geometric approach, the model structure is constructed using a left Bowers field localization.
Please repeat where from we transfer model structure in
Yeah, so
domain
here
of
it's always transferred from the along the forgetful functor. So for example, you would have a model category of infinity spaces, and it would admit a right adjoint the forgetful functor to spaces. Whatever your model for spaces is, for example, you can take simplicial sets with a conquilling model structure, or you could take the topological spaces with the equivalent Serre model structure.
What about intuitive? It means that the spaces encode infinite loop space structures, yeah? So, what?
Yeah, I mean, an infinity space is basically by Skashev's or May's theorem. I forget which one it is. Sorry, the same as a loop space. So every A infinity space has a canonical D-looping, and the loop space of the D-looping will be weakly equivalent to the original space. So in that respect, it's precisely the same. Yeah. So So yeah, the A infinity is, if you want, yeah, the canonical example of an A infinity space would be loops. The space of loops of a topological space X, for example. You can multiply loops, because loops are just maps from, say, the interval 0, 1 to X. And you can multiply two loops together by concatenating them. So you have two such maps, and you concatenate them, but the domain of the new map will be an interval twice as big. So you have to rescale the domain to a smaller interval. And now you see that if you write down the associativity constraint, the associativity will not be satisfied strictly, but only up to homotopy. So you have to introduce a structure of an A infinity space. Yeah. All right, so just to finish the topic of comparison of the two models, the remaining features, or the difference, if you want, is that, well, A infinity spaces are fairly easy to understand. Their definition, what I just mentioned on the previous page, for example, when we discussed how you have this multiplication, which may be associative up to some coherent higher homotopies. Well, in principle, that is fairly intuitive to understand. But it's also somewhat difficult to encode examples because of you have to specify all this data. And the situation with delta spaces and gamma spaces is basically the opposite. The definition may not be the most easy or the most intuitive definition, but once you understand the definition, it's easy to encode examples. Are the limits a question from the audience? Are the limits in both approaches easy? Yes. Limits in both cases are easy, which is why I didn't mention them. But in both cases, limits or homotopy limits will be computed object-wise. So here, homotopy in the algebraic setting, limits and homotopy limits will be computed on the level of underlying objects. So here the forgetful functor preserves limits, or respectively homotopy limits. And in the geometric setting, they are also computed on the level of underlying presheaves. So again, limits are object-wise. This time there is no need to apply the localization functor because limits of local objects will again be local. So limits in both cases are easy, and that's why I concentrated the review on comparison of colimits. So limits are typically just straightforward. All right, so let me recall, just to motivate, the definition of a Siegel space, which may not be the most intuitive possible, the most intuitive of all definitions. Let me very briefly review the constructions associated to monoids in the category of sets. So just the usual monoids that you are familiar with your abstract algebra class. So we have the category of monoids, which I denote by monoid. We also have the category of small categories, cat. And there is a de-looping functor, capital B, which takes a monoid and turns it into a category with exactly one object. So that's what B is. And from the category of small categories, you have a nerve functor that lands in simplicial sets. And the nerve functor is a fully faithful functor, so that means morphisms of categories, like I could say functors, are in fact the same as morphisms of the corresponding simplicial sets. And this would make the nerve functor into an equivalence of categories. In fact, it does make it into an equivalence of categories once you restrict its codomain to its essential image. So if we were to restrict the codomain of the nerve functor to its essential image, then the nerve functor would be an equivalence of categories. So naturally, we are interested in describing the essential image of the nerve functor. And as it turns out, and basically this was already observed by probably Grothendieck, is that the essential image of the nerve functor is comprises precisely those simplicial sets X that satisfy the Siegel conditions. What is a Siegel condition? The Siegel conditions say the set of m plus n simplices admits a map to this fiber product here. M simplices, a set of m simplices, and n simplices over 0 simplices. And here, let me tell you what how this map is defined. Well, to define a map to a fiber product, you must define a commutative square, right? So I would have to specify a commutative square of this form. And you can already guess what these maps should be. This map, the top map, will take an m plus n simplex and take its phase corresponding to the first m plus 1 vertices in the m plus n simplex. And the left map will do a similar thing, but it will take the phase corresponding to the last n plus 1 vertices. And this map will, the right map will extract the terminal vertex in an M simplex, and the bottom map will extract the initial vertex in an N simplex. And you can sort of see a picture that illustrates this here for the case of the nerve. In the nerve, an N simplex is just a chain of N composable morphisms. So here you see a 3 simplex, here's a 3 simplex here, and here is a true simplex. I guess I should make it a true simplex. A chain of true composable morphisms. And here on the left side, you have m plus n simplices. So in our case, m equals 3 and n equals 2. So these will be chains of five composable morphisms. And these maps in this commutative square, the top map will extract the first m morphisms, like here. The second map will extract the last n morphisms, like here. And since the middle vertex, the vertex along which you join, will be the same here and also here. This is precisely the x0 along which they have to match. So the Siegel condition is very naturally satisfied for a nerve. As you can see already from these pictures. And Grothendieck's insight was that that's the only thing you need. if you have a simplicial set that satisfies the single conditions, then you can recover a category. In fact, this construction may be important enough for me to perhaps offer you some details. So suppose X is a simplicial set, and X satisfies, and let me pull the single conditions here, satisfies the single conditions so these ones, the fact that this map has to be an isomorphism, then there is a category C whose nerve is isomorphic to X, and C is very easy to construct. Objects of C will be zero simplices in X. Morphisms of C will be one simplices in X. The source and target map that take a morphism as an input and produce a morphism, an object as an output. These will be maps from x1 to x0. And there are precisely two such maps. The zeros, the first phase map will be the source, and the zeros phase map will be the target. Right? If you think of a one simplex as an arrow, which you also interpret as a morphism, and the zeros phase map extracts the terminal vertex, so that's the target. And the first phase map will remove the first vertex, and it will extract the initial vertex, so that's the source. We also have the map that accepts an object as an input and produces the corresponding identity morphism. Oh, that's precisely the zeros degeneracy map. Takes a vertex as an input and produces a degenerate simplex from this vertex to itself as an output, and that's precisely the identity morphism. Next, the composition map. How does a composition work? Well, composition in a category accepts true morphisms as an input. And these morphisms are not arbitrary, they have to match, right? So it's, you think of them, so here is a picture. And here's one morphism, here's another. The target of the first one has to match the source of the second one. So this, in fact, will be a fiber product over objects. And the true projection maps will be respectively the target map and the source map. Oh, yeah, sorry, I guess here I wrote it from composition from left to right. My apologies. It should really be the opposite order. Yeah, so and this should have a map to morphisms, which would be the composition. Well, let's see. The object on the left is x1 times x1 over x0, and the structure maps here the two legs will be the first and the zeroth phase map respectively. But that's precisely the object that occurs in the Siegel condition. If you take the Siegel condition for m equals n equals 1, then this pullback here is precisely the pullback of these two maps here. And so this means that we have an isomorphism from X2. On the other hand, X2 admits a map to morphisms, which is the first phase map, right? So you think of an element of X2 as some kind of a triangle. And the reasoning behind taking the first phase map is here you have some F, here you have some G, and on this phase you have the composition. And this is precisely the first phase, the phase opposite of the middle vertex. So the composition map can be in general defined as the inverse of the Siegel map here, followed by the first phase map. And it's not very difficult to show that the resulting composition is associative and unitary. Which again would use Siegel's conditions, this time in 1 degree higher also. And yeah, this is how you recover a category from its nerve. All right, any questions about this construction or what we had in the previous slide before we move on to the homotopy coherent setting?
And are there any other examples?
Any other examples of what?
For Siegel conditions.
Examples for, well, we will have some concrete examples of Siegel spaces a bit later. And I guess in the theoretical constructions, I mean, we'll see a more sophisticated version of these examples in a moment when we do gamma yoga spaces and gamma spaces. So there will be more examples. Just a second, yeah. Okay, so let me now see how the story changes in the homotopy coherent setting. In fact, almost everything turns out to be at least exactly the same in the formal way. Now we want to encode some category of homotopy coherent monoids. And since I'm too lazy to write the word homotopy coherent, I simply will prefix everything with infinity. So infinity here is a scaling for homotopy coherent. So we should have something like homotopy coherent monoids. These should embed into homotopy coherent categories via the de-looping functor. And there should be some homotopy coherent version of the nerve functor. In fact, in some settings, it's called precisely the homotopy coherent nerve, and it should land in simplicial spaces.
Also, I want to ask a question about previous section about Siegel conditions. What about category of CV complex? C double B complexes category. They are satisfied to Siegel conditions or not with base point?
So what kind of Siegel object do you have or simplicial object do you have in mind? Maybe I should ask first.
in general, it is not satisfied in category.
CW complexes
Yeah.
do form a topological category. It's a category enriched in topological spaces. Well, at least if you impose no, it's fine. Yeah, they do form a category enriched in topological spaces, which means and every category enriched in topological spaces will canonically give rise to a single category. Because of course, if you have a strictly associative composition, then the strictly associative composition will induce of course, a homotopy coherent composition. So in that respect, you do have a single category that you can obtain from any topological category. So maybe in that sense, the single conditions will be satisfied here.
As I understand, is it possible to construct single category with single conditions for any topological category? Yes.
Yeah, the topological categories embed into single objects or complete single objects in topological spaces. Yeah.
Okay.
All right. Yeah, so since I already mentioned that the near functor is going to land in simplicial spaces, now it will come very naturally to us that the essential image of the near functor presumably should be simplicial spaces that satisfy the homotopy coherent version of the single conditions. And these, in fact, are the original single conditions that single defined, more or less. And the only difference, of course, we can write down exactly the same map, more or less, or here's the same type of a map, will be induced by exactly the same commutative square as in here. And the only two differences now is that instead of the ordinary pullback, I will take the homotopy pullback. And instead of requiring the map to be an isomorphism, I will require it to be only a weak equivalence. And that's it. That's the definition of a single space, which I probably should have mentioned here. So this condition defines single spaces. So at least now it shouldn't appear as if it appeared out of the blue, and I think it should be very well motivated now, this definition. So we are motivated by the idea of replacing a set of morphisms with a space of morphisms. When we pass from sets to spaces, pullbacks become homotopy pullbacks, and isomorphisms become weak equivalences. So in that respect, the definition should appear very natural to you. Okay, so next question to ask here is how to encode such a condition in a model category. And you may ask, well, what's the problem? I mean, it's of course very easy to write down this map in any model category and just look at objects X that satisfies this property here. But one problem is if we do single them out in this way, the result will not be a model category for really stupid reasons, because objects that satisfy this property are not going to be closed under finite limits or finite colimits. And here I mean the strict limits or strict colimits. And in some cases, at least, we would like to have an honest model structure. An observation to make here is that this condition here is basically formulated as a property involving homotopy limits. Right? You are simply saying that a certain commutative square is a homotopy Cartesian square. It's a homotopy limit square. And of course, such this property would immediately imply that objects satisfying this property are closed or stable under homotopy limits. If you take a homotopy limit, the homotopy limit of a diagram of objects that satisfy this property, then the homotopy limit is again going to satisfy the same property because homotopy limits commute with homotopy pullbacks. Simply because homotopy pullbacks are special type of homotopy limit, and homotopy limits commute with homotopy limits. So every time you see a full subcategory closed under homotopy limits, you should be thinking about reflective subcategories and Bowles field localizations. And the reason for that, in fact, it is possible to formulate this in a precise way if you have a locally presentable category and it has a full subcategory closed under small limits. And let's say it's also closed under sufficiently filtered colimits. Then this subcategory is a reflective subcategory. The inclusion functor has a left adjoint. And that's exactly what we see here. The full subcategory is closed under homotopy limits. And of course, it will also be closed under filtered homotopy colimits, because filtered colimits commute with pullbacks. So yeah, we certainly do expect this condition singles out a reflective subcategory, or in other words, we expect that it can be encoded by a left Bowles field localization. That's exactly what we are going to do now. So the model structure and Siegel spaces, meaning simplicial objects in simplicial sets, or even more precisely, the category of functors from the opposite category of delta to simplicial sets. This category is equipped with a model structure in two steps. In the first step, you will construct what is sometimes called a global model structure. On simplicial presheaves, and you are basically free to pick any your favorite model structure here. It could be a projective or injective, meaning respectively fibrations or cofibrations are defined object-wise. Either of those will work just fine. In some settings, the projective model structure is more convenient, like maybe for concrete complications. In some other cases, the injective structure is more convenient, for example, for theoretical developments. And in the second step, you are going to enforce the Siegel condition here by performing a left Balanced localization at the so-called Siegel maps. These are the maps that induce the Siegel maps here once we start mapping from these objects to some fixed presheaf f or x. And so let me first say what the maps are. So y, recall, denotes the Yonage embedding. So these are all representable presheaves here of various simplices, namely the M simplex, the N simplex, and the M plus N simplex. This is the homotopy pushout. So it's a homotopy pushout, which in this case, it will turn out this homotopy pushout can be computed as the ordinary pushout, which is not always true, but it is true in this case. Basically, one way to see it is to observe that these maps in the diagram will be injective cofibrations. And this object here is just a vertex, or in other words, the terminal presheaf. And it includes into the M simplex and the N simplex as the terminal, respectively, initial vertex. And finally, to specify a map from a pushout into the M plus N simplex, I have to specify maps from the M simplex and N simplex separately. From the M simplex, I will simply include it as the first M plus 1 vertices. And for the N simplex, I will include it as the last N vertices, N plus 1 vertices. Okay, and the observation to make here is fibrant objects in the resulting model structure are precisely fibrant presheaves in the global model structure. So in the case of the projective model structure, these will be precisely presheaves of Kahn complexes. And these fibrant presheaves must further satisfy the Siegel condition here. And the proof is really simple. Being a fibrant object in a left Balanced localization amounts to being fibrant in the original model structure, which in our case is a global model structure. And furthermore, you must be a local object. So in other words, you must be a local object with respect to the Siegel maps here. And how can we see what does it mean to be a local object with respect to such a map? Well, let's pick some arbitrary presheaf, simplicial presheaf X, and start mapping this map is domain and codomain into X. Or more precisely here, which is a derived mapping space. And when you map, for example, a representable presheaf over the M plus N simplex into X, since the representable presheaf is projectively cofibrant, you can compute this derived mapping space as the evaluation of X at the M plus N simplex. And that's why on the left side, once I map the codomain into X, I get the value of X at the M plus N simplex. Now, what happens if I map this homotopy pushout into X? Well, the derived mapping space functor sends homotopy pushouts to homotopy pullbacks. So that's why you get a homotopy pullback here, and it sends a maps sends a representable pre-sheaf to the corresponding evaluation. So you see that once we map into X, we get precisely the Siegel map, and being a local object amounts to saying that this map is a weak equivalence. And that's precisely the Siegel condition. And this
sorry, maybe a
Yeah,
stupid question. So
no,
doesn't it, so the homotopy pullback pulls through the right-derived mapping space, or the right-derived hom?
homotopy push out, you can pull it out,
homotopy.
yes, it becomes a homotopy pullback, yeah.
But then again, so the Yoneda embedding, I mean, the Yoneda lemma only holds for the non-derived functor, depending on the model structure, right? So because we have to replace the Yoneda embedding.
Maybe I should phrase this at some point as a more precise statement. If you want, you can call it the derived Yoneda lemma.
Mm-hmm.
It talks about, I guess, pre-sheaves in a model category, for example, could be a simplicial pre-sheaf. Or not even necessarily simplicial, could be valid in any model category, really. And you have some representable object. So I guess I already called it F. Maybe I should keep calling it X. You have some representable object. Let's call it A. It will be a representable. A is an element on the object of C. And you are interested in the derived mapping space from the representable pre-sheaf of A into X. Well, here is one way to compute it using only the tools we have learned so far. And one tool we learned so far is that there is a projective model structure in the category of simplicial pre-sheaves. And in any model structure, the derived mapping space can be computed as the ordinary simplicial mapping space. So this category is a simplicial model category from the co-Phi replacement of the source to the Phi replacement of the target. Now, in the projective model structure, this representable pre-sheaf is already co-fibrant. This means the co-Phi replacement can be chosen to be the same, or the same as the representable pre-sheaf itself. Now, the ordinary enriched one-categorical Yoneda lemma tells us this is the same or isomorphic to the value of the Phi replacement on A, which is almost what we want, which is the value of X at A. But what about this Phi replacement? Well, recall that any Phi replacement accepts a weak equivalence from the value itself. And being a Phi replacement is precisely what guarantees this map is a weak equivalence. In fact, in a model structure, it will be an acyclic cofibration even. So altogether, if we combine everything we see, I constructed for you a natural canonical functorial weak equivalence from XA to the derived mapping space.
Yeah, and the trick is then that the derived mapping space doesn't depend on the model structure, but only on the weak equivalences, right?
Yeah, pretty much so. Yeah, I mean, in fact, yeah, you are correct that, of course, I could have mentioned just the weak equivalences here. Yeah, and that would be sufficient. Yeah. But in this case, we actually very creatively used the fact that we are free to choose a model structure we chose the projective model structure, which immediately allowed us to use the Yoneda lemma in the one categorical setting by observing that the representable pre-sheaf is cofibrant. And in principle, of course, it is also possible to avoid referring to model structures at all, but maybe the argument would be a bit more difficult. Yeah.
Also, maybe one more question, if that's fine.
Mm-hmm.
So there, in the slide before, we had this nerve of spaces or nerve of infinity categories, I think. So I don't know if I missed it, but did you say what this functor n is here?
No, we will start discussing it soon, but
okay.
But in the case in the case of when we implement this using implement this middle term as a left Bowles localization, then this neural functor can be in fact thought of as a the right adjoint in a Bowles localization. Yeah. So let me actually yeah. In fact, we are going to discuss it more or less right now. Let's see. So here. Okay, yeah, maybe I should have discussed this a bit more explicitly. Let me insert another page here. Yeah, so let's collect what we have learned so far. So we have the projective model structure on simplicial pre-sheaves. Or it doesn't have to be projective, could also be injective. We have the localization functor to the localization. So it will be the same underlying category and the same cofibrations, but now the weak equivalences will be the, if you can, we can probably call it the Siegel weak equivalences. And in the, maybe I should pull the informal diagram on the left, and unfortunately the order is now reversed. Let's see. Yes, here. This is a model, what I call for simplicial spaces. And this, well, it's almost, I mean, I'm stretching things a bit here. I should include one more condition, the completeness condition. But this is almost a model for what I call infinity catch. And this functor L is of course the left adjoint to the nerve functor. So the right adjoint you think of it as a right equivalent functor implementing the nerve functor. So let me call it R. Well, I mean, the confusing part here maybe is that on the level of underlying categories, both of these functors are identities, which may be extremely confusing, but that's how left Bowles field localizations work. And the thing to keep in mind here is that you really are interested in the derived functors here. And so one way to say that what the nerve functor is it really should be the right derived functor of this right adjoint. So let me call it maybe curly R. So it's right derived functor, which, if you may recall, we previously defined as a precomposition with the Feynman replacement functor. Oh my god, this is terrible. The Feynman replacement functor will also denote by R. So let me pick a different letter. This is too much. Let's call it some other letter. Let's see. So R is bad letter. So I don't know. T, T I think should be fine. And the right-derived functor is computed by precomposing with the finite replacement functor. And the finite replacement functor here, it does some non-trivial things, right? It takes an object in this category, which is a functor from delta opto sets, and it forces it to satisfy the single conditions. So in the model with left pulse field localizations, the homotopy coherent nerve functor is implemented by basically the finite replacement functor that replaces an arbitrary simplicial object in simplicial spaces with a weakly equivalent Siegel space. Now, if your input data already satisfied the Siegel conditions, then this construction basically does nothing. And so you may ask, well, what's the point of calling the do nothing functor the homotopy coherent nerve functor? Well, the point here is that in this setting, we are encoding infinity categories. They are basically encoded by their nerve, by their homotopy coherent nerve. That's one way to interpret what is happening here. So you should not be too surprised that if you encode an infinity category by its homotopy coherent nerve, then the nerve functor is going to look basically trivial, other than the finite replacement. This is a finite replacement, but otherwise it's just the identity functor. And that's just a feature of the encoding you chose here. Yeah, so the adjunction, the nerve realization adjunction here. So the left adjoint to the nerve functor is always called the realization functor, no matter what. And the nerve realization adjunction here on the level of underlying functors is just identities, but on the level of derived functors, it will be something not entirely trivial. So the left adjoint functor will be simply the cofinite replacement functor on simplicial pre-sheaves. So if you pick the injective model structure, for example, then all objects are cofibrant. So it's not necessary to do anything. Whereas the right adjoint, that will be given by the finite replacement functor. So that's just the localization functor. Am I just looking at? Yeah.
This looks very much like the nerve realization adjunction, but still the classical picture, like you have like you explicitly construct the nerve as like saying, well, this nerve realization adjunction you put in like, I think, well, you have this left Kahn extension stuff along the unit embedding of a functor, and then this is left adjoint to the left Kahn extension to the other pair, like switching the pair and stuff. And I don't see how this immediately applies to this. Maybe this is, I don't know.
Yeah, this is exactly also how it works here. So, I mean, in general, yeah, it is correct that if you have some arbitrary category or infinity category C, you can produce a nerve functor by sending an object of C. So here's perhaps some simplicial objects with values in spaces or simplicial sets. Well, the nerve of some object X, its n simplices will be some kind of maps in C from whatever simplicial object, co-simplicial object, sorry. So as an input gate to the nerve construction, you have to specify a functor from delta to C, which, let me call it, I don't know, like, let's call it S, right? So here you would take maps from Sn to X. And since S is a covariant functor from delta to C, mapping it into X will produce a contravariant functor from delta to simplicial sets or whatever C happens to be enriched in. And that's the nerve functor. And its left adjoint. It's called the realization functor. And the realization of some F will be simply what is called the weighted colimit or the co-end or the con extension, depending on your preference. It's all the same, really. So let me write it as a weighted colimit. Over this category. But if you are interested in like other formulas, you can find all of them on the NLab page. Like for example, you can write this as a coeng. I'm not even sure how to write this properly. Or you can write it as expand this as a con extension because any functor from delta to C will have you have a Yonega embedding and left con extending this functor S along the Yonega embedding produces the realization functor. So all of those descriptions work. Question?
Please, may you reveal about coherent structure, some intuition? I'm trying to recognize why is it denoted as integral notation. I'm trying to.
Oh, this is just called a coeng.
Yes, and why is it defined in such a way?
Yeah, it's the definition. I mean, in this context, is basically the same as a weighted colimit, but I mean, the point is that there's a universal property that a coeng must satisfy. So the universal property is basically very easy to, let's see. I mean, in general, to talk about coends, you will talk about you will consider a functor of this form. Let's call it F, and the coend of F x comma x with respect to x is by definition an object equipped with a collection of maps. So for any what's called any object A in C is you have such a map, and these maps, let me call it, I don't know, iota A. Iota A must satisfy the following condition. if you have another such f of bb, here you have iota b, and here you have a map from A to B, and this map sends f of AA to f of AB. Hope I got this right. Yeah, so it goes in the opposite direction. F of BA maps into f of AA, and it also maps into f of BB. This square must commute. And the universal property tells you that if you have such a system of maps, iota, its universal property is for any other such system of maps, iota prime, you will have a unique map from the co-end to the other apex. So it's kind of like a co-limit type property, but here instead of, so you have an analog of the injection maps for co-limit, and you have an analog of the universality property for a co-cone. It's only that the definition of a co-cone is replaced by this definition of what is called a wedge. So cones are replaced by wedges. And
as I understand, intuition is the following. It is used just for collecting some maps, some morphisms, yes, and notation is used as for integral just for this purpose, yes, for the collecting of a such.
Well, yeah, I mean, it's just using a way to sort of fuse the data of various objects obtained by evaluating f together. Yeah, I mean, that's the only point of using the integral sign here. Yeah, so it fuses all these values together in a sense. Yeah.
Is it possible to descend these things to ordinary integral?
I'm not sure if I saw a specific.
I think there is something like this in Fosco's book.
In whose book?
There's Fosco Loregian or so, and he has like a book on coends. And there is an example where he defines a category, takes a coend over this category, and the universal property of the coend is then precisely Stokes' theorem. So it's quite a nice, so something like this. But
maybe
post
in our Discord for everybody to see this link after the class, maybe.
Yeah, sure.
I would be
interested.
Yeah.
So maybe the question I was asking. So this is the classical construction that you wrote down before that with this thing, and then maybe I can also ask the question after the lecture so that you have more time, if that's
it's fine. I mean, we are approaching the end, I guess. Let's see, what would be a good time to stop? Actually, let's see, do we have anything else for today? Well, I guess, in fact, since it's 10:30 already, this is, I think, an excellent time to stop and transition into like a questions stage. So,
okay.
So please go ahead.
Mm-hmm. So because you are mentioning, can you go further up with this?
Yeah, sure. Let's see. So let me.
Yeah.
Okay, so here.
So where there's a junction was the nerve realization adjunction in the homotopical. Yeah, this one. Here. Yeah, precisely. So yeah. I would assume that like the realization functor should be. So usually when you look at the geometric realization, or not the geometric, but the homotopy category, which is defined by means of the realization functor, then you have the left Kahn extension along the Yoneda embedding of the inclusion functor of the simplex category into the category of categories.
Yes, right? And in fact, that is exactly correct. Yeah, I mean, you can prove that What you can prove here is that the left derived functor of L is weakly equivalent to the homotopy left conic extension of the you will extend on the Young embedding, and what you will extend will be the functor you have.
So this is the same functor. This is the same inclusion of the simplex categories into infinity categories. So you just take.
Yeah.
You interpret.
So here,
this was my question. Okay.
Yeah. So the functor. So it will be the functor from delta to here. This functor will send an object n to basically its representable pre-sheaf, which you interpret as an n simplex is now interpreted as a composable chain, or as a category, if you want, consisting of a composable chain of arrows. That's the object with respect to which you realize. Yeah.
Okay, perfect. Thank you.
Yeah. Okay, more questions? All right, so next time we are going to further refine this discussion and actually define stuff like infinity monoids using Gauge spaces, which involves one more very simple condition. Siegel categories, complete Siegel spaces. We'll discuss how to encode infinity groupoids and infinity groups. All of these will be encoded by an additional morphism that you will add to your left Bowles localizations. And we will then examine a whole bunch of examples, including ordinary monoids, simplicial monoids, and then even more difficult ones, like how to encode various homotopy coherent monoidal structures using this formalism of Siegel spaces. This is not an entirely trivial construction. So that's what you can expect next time. And I guess thanks for listening today, and do feel free to ask more questions in our Discord server, just in case you have any. So, and see you next time on Sunday at the same time.
One moment, I would be very grateful if someone to ask. Also, Alex, may I ask on my last question about Koi, and also if you have some good reference, I would be very grateful.
Oh, a reference, I think, so there's this book by Fosco. I honestly forget what is his final name. It used to be called like this as the...
I think nowadays it's called Cohen calculus, and I can send it in the Discord group.
Okay, yeah, that would be very nice, yeah.
And also, I think it's just to say it, it's example 1.4.5 in the Cohen calculus book, which is about Stokes' theorem, is about Cohens. This is the title.
Interesting. Yeah, I recall it used to be called something like this is the Cohen, my dear co-friend, which was kind of funny, but I guess the publisher forced him to change the name.
Sorry, example 1.4.5, not 1.5. So 1.4.5.
1.4, yeah, so 4.5 like this. Okay, thanks. All right, yeah, more questions?
Thanks for the lecture, Dmitri.
Yeah, you're welcome. Yeah, see you guys next time.
Thank you for your lecture.
Bye.